due to assimilation, that most magma never reaches the surface. That assimilation process uses up a lot of that magma's heat energy. So the closer it gets to the surface, that magma loses heat to melting the surrounding rock, and it solidifies as it loses temperature. Now, as that material is rising, we get an added benefit. Hot, rising magma. In that magma is a lot of gas. Gases like carbon dioxide, sulfur dioxide, nitrogen, hydrogen. These gases are released when minerals melt. When the minerals melt, their atoms all separate from each other. And since many of those elements of those minerals are oxygen and carbon and sulfur and hydrogen, when they are released from their chemical bonds in the minerals, they go back to being gases, elemental gases. Also in this magma, there's always a significant quantity of water. Water was very likely involved in the original production of the magma. Remember, water helps facilitate the melting process. And again, many minerals contain the elements oxygen and hydrogen. So when those minerals melt, those elements are able to find each other and recombine, and they form water, and under these temperatures, that water becomes steam. The steam is going to be constantly bubbling out of the magma and trying to escape to the surface. That steam is responsible for helping to break apart the bonds holding the atoms together in the minerals. So that steam contains a lot of dissolved elements. It contains dissolved gold, dissolved iron, dissolved zinc, dissolved lead, and that steam takes those elements with it as it tries to reach the surface. And that steam will follow all of the cracks and crevices and nooks and crannies in the surrounding country rock. And on the way to the surface, that steam is going to be cooling off. And as the steam cools off, it will leave behind the elements that was in it. So as that steam cools off, new minerals are going to form, are going to start crusting up inside all those nooks and crannies and passages wherever the steam goes. Not too often you get to use the word crevices. Good word. When miners are tunneling, that's what they're looking for. They're looking for where the steam went. They're following those cracks and fractures that that steam went, left behind those materials. Oftentimes, this is how we get vast concentrations of metals like gold, silver, platinum, lead, zinc, tin, iron, copper. It's a lot easier and a lot cheaper to tunnel through where the steam went, thank you, than to just try to mine the whole rock and sort it out at the end. Who here's got brothers and sisters? Brothers and sisters? Your parents ever buy like a big carton of ice cream that's got some kind of swirl in it? You know, it's like hot fudge swirl, or caramel swirl, or marshmallow swirl. And you know as soon as that's in, you know you got to get to it before your brothers and sisters do, because they're going to just get a spoon and just tunnel it out. They're going to go through the whole box of ice cream, just follow me where the caramel goes, and then you get to the box, it's all vanilla. Yeah. Well, the miners are doing the same thing. They're tunneling. They're following the caramel. They're following those veins with the steam wind and left behind those valuable materials. These types of steam deposits, they're called hydrothermal deposits, which pretty much translates into hot water, hydrothermal, hot water deposit, left by the steam. Now these deposits and these plutons, these masses of intrusive igneous rock, they form at great depth in the earth. They'll form at 5, 10, 20, 60 miles deep. Now, fortunately for us, we have active plate tectonics on this planet. And when the plates move around and they collide with each other, they lift mountains. And in mountain building processes, these deeply formed rocks get lifted up closer to the surface. And that makes it a lot easier for us to get at them. So we can mine them for these minerals and elements. And of course, we also mine these huge, intrusive igneous rocks for building stone, countertop, monument stone, pavers, flooring. The intrusive rock has a big, sparkly crystals, and we want that for countertop and monument stone and all that. Any questions? If you're looking for me some Saturday, I'm usually at Home Depot or Lowe's, where they have all the big stone slabs outside of the door, and I'm just like looking at it. You know, usually something. So the security guards come out.
Yeah.
Geologists do this. They just do this. Cheryl Thompson, the other instructor, she calls me some afternoon. She says, "Oh my gosh, I just got back from Fairfield Commons Mall." This was a while ago. And she said, "Have you ever been to JCPenney?" And I'm like, "No." She said, "You gotta go." I think what was their sale? She said, No. The stone on the front of the building is vehicular granite. You got to, oh my gosh, it's awesome. You got to go see it. So I'm like, okay, cool. So I was up there one day, and I'll check out the stone at JCPenney, right? So it's an ovicular, it's what they call ovicular granite, because there are rings of quartz around the feldspar crystals. It's the same kind of stone that's at the cash registers down in the cafeteria. It's the same stone. So they call it ovicular. It looks like an eye. And we don't know why it forms that way. We're working on that one. But the best deposits come out of Scandinavia, Norway, Sweden, Finland. So it's, you know, yeah, try shipping rock. Yeah, it's expensive. So it's gorgeous. So I'm there at JCPenney, and you know, oh, cool. I'm looking at the stone, and I catch out of the corner of my eye, there's in the little entryway, there's a security guard, and he's like this, looking at me. So finally he comes over and he starts talking to me, and I show my eye, and I'm geologist, blah, blah, blah. And someone told me this, I'm just here looking. So then there are two of us, and we're going, and people are coming in and out of the store like, what is going on? So, but yeah. We'll go to conferences that are like at big fancy hotels and stuff, and we women will come out of the restroom and go, oh my gosh, you gotta go in there and see the marble partitions they have between the stalls and the countertop. I don't know what it is, it's some kind of, I think we just do that. It's a thing. We'll do that downtown too. If we're walking around the building, we'll stop. Ooh, is that garnet? Building. It's unavoidable. Are there any questions? Other than where's the drop line?
Have you ever been arrested for that?
Not yet. Not yet. We'll see. Not yet. Oh, no. You got to see it as a teachable moment. I was also in one place I was waiting for somebody. I was looking at the furniture, and they had these coffee tables with the stone top, but the stone top was just like a really bad photograph of what stone looks like, and then it was like a sticker, it's like a laminated looking thing. And the sales guy comes up to me and goes, "That looks just like real stone, doesn't it?" I said, "Well, no, not really." He got mad at me and walked off. Challenges. I know what the real thing looks like. That's not it. Well, occasionally, I have to throw out an image galleries. That has happened to me. That's another story. So, volcanism, occasionally, it's comparatively rare. It's about 80% to 90% of all molten rock doesn't see the light of day. But occasionally, if there's a crack or a fracture or a fault or a pipe or some opening that allows this material to rise to the surface, it's going to, and it will spill out on the surface, in which case then we have volcanism, which is extrusive igneous activity. And that will produce a volcano. Now, a volcano is any opening in the crust that allows molten rock to reach the surface. It could be a hole, it could be a tear, it could be a crack or a crevice. It could be any opening. Now the word volcano, ouch. Let's fix this problem. There we go. Well, the word volcano also refers to any kind of structure that's built up around that opening by what comes out. So the lava, any material that comes out of that opening can pile up around it, and that's also, that pile of collected stuff is also called a volcano. So volcanoes are formed from molten rock that reaches the surface. Is all molten rock the same? No. How many types of molten rock are there? More than one? Less than 10? Less than 5? Yes, 4. That was in the class last week, so maybe a little fuzzy. Remember we had our ultramassive? Yeah! I think that's what food No, that's probably what happened. Ultramassive. Intermediate. Now these types of molten rock, they're different from each other. They're different composition, they're different temperature. Composition and temperature are going to give them different physical properties. They're going to behave differently. Different types of molten rock will produce different volcanic activity. not all volcanoes, they're not all equally dangerous. They're not all equally threatening. They're not all threatening necessarily the same way. And that's mostly because of the type of molten rock they're made from. We do have some kinder, gentler volcanism. So now, if we look at volcanoes, we basically have two most common types. We have shield volcanoes and composite. There are others, but these you'll see most often. These are our most common. Shield volcanoes are called that because from the side, in profile, they look like a domed shield. They are much wider than they are tall. So they are rather short and wide. Nature likes a balance. So if you have one, you probably have the other one, the opposite. So composite volcanoes are going to look very different. Composite volcanoes are called that because they're made of alternating layers of lava flows and ash. They're also known as stratovolcanoes. Strato meaning they're in layers. Composite volcanoes are tall and narrow, often with very steep sides. Now, a shield volcano is going to be wide but low. Then what does that tell us about the molten rock? It's telling us that when that stuff comes up out of the ground, it must be loose and runny, because it comes out of the hole and it spreads out more than it piles up. It's like pouring water out of a glass onto the table. The water's just going to spread out over the table. You're not going to expect it to all pile up at the bottom, are you? I don't. So shield volcanoes are made of a more loose, runny, thin material. Composite volcanoes, on the other hand, tell us something very different. In the case of a composite or stratovolcano, everything's piled up around the opening. So that tells us that these volcanoes are made from molten rock that does not flow. Doesn't flow well at all. It's like squeezing toothpaste out of a tube, just all piles up around the opening. Thick, gooey, sticky, sticky. Just real thick, gelatinous. But actually not a spell. Yeah, I can spell gooey. It's not spelled occasionally. It's not spelled. Not even some of the time. Thick, gooey, sticky molten rock. Thin, runny molten rock. Scientists don't like going around talking about things like there's thin and runny or gooey and sticky. This doesn't sound like we know a lot. So we have our own names for that. We call that viscosity. Viscosity is a measure of how easily fluid flows. And it's kind of a backwards word. I'll explain that. Something that flows easily. If it does flow, it is non-viscous. Flows easily, that is non-viscous.
Easy way to think of it is viscosity is density. So if the density is more, then it's going to flow slower. If the density is less, it's going to flow faster.
Yes, you can look at it that way.
Density of a fluid.
Yes.
Oils go with it, like oils for cars. And
Yes.
That's how they judge, that's how they rate oils.
It's just got to be able to, yes, it's got to be able to flow through the engine parts. Yeah. Otherwise, it's gummy. Gummy. That's a good word. Gummy. Gummy. Ew.
That's because the viscosity breaks down.
Yes.
From heat and pressure.
And the air. Exposure to air does that. So if it flows easily, non-viscous. So shield volcanoes are made with non-viscous molten rock. Composite volcanoes are made of viscous, to very viscous. Honey, molasses, shampoo, those are viscous fluids. Now, I already had a little bit of an oil example. I got another example. Where are my ketchup can stay on the countertop people? I'm getting fewer and fewer of those as the years go by. Where are my, no, ketchup must stay in the door of the refrigerator people? Yeah, okay. Where are my, I don't care, it's ketchup people? Yeah, there you go. But now, you know from experience, I'm sure, that the advantage of having the ketchup on the table is that when you need to use it, it's going to come out of the bottle. If it's been in the refrigerator, you're going to have to do this with it. Get it out of there. That's one of the reasons why most everyone in this room, I'm sure, somewhere in your bathroom or refrigerator door, has something in a bottle upside down. Because it's thick and you want to get it to flow to and you're trying to get it to go to get the rest of it out of there because it's conditioner that you got at the salon for $50 and you want all of it out of there, right? You come home from a long day, you get the bowl of ice cream and you get the rest of the chocolate topping or caramel topping out of the refrigerator. That's not going to pour out of that jar. You got to use it first. Right? Or just say, the hell with it, get a spoon. It depends on how hard your day was. When you get to a point, and I'm sure some of you have been here, you know the topping that's in the squeeze bottle, and you can hear it in there, but it won't come out. You ever get the kitchen scissors? You just cut it open and... Yeah. You know you got a long day. That's right.
Check it out. Just pour it out.
It's the same thing with molten rock. That viscosity, as it is for engine oil, is dependent on temperature. The hotter that material is, the easier it's going to flow, the easier it will move. So shield volcanoes are going to have very hot lava. Shield volcanoes can have lavas that are well over 2,000 degrees Fahrenheit. Hot, high temperature. Composite volcanoes, they have much higher viscosity. So their temperatures are going to be medium to low. There's another thing that will impact viscosity, and that's the composition. There's a reason why honey flows more slowly than water. Honey's got sugar in it, so it flows more difficult, with more difficulty. It's a different composition. That's what you can always tell the difference between hot fudge and chocolate syrup, because the fudge has more fat and sugar in it. So it's thicker, it's more viscous, it's a different composition. When looking at molten rock, the biggest thing we're looking at is the silicon and oxygen content. Non-viscous has low silicon and oxygen, but high iron and magnesium. That's silicon and oxygen. You've got to watch out. Silicon and oxygen as elements are BFF. They will seek each other out. They will find each other. They will bond with each other very readily. And they make all these little cliques, and these little gangs, these little groupings in the magma. It's kind of like, you run out of class because you have to hook it to another class in another building, and you only have, a couple of minutes. And as you're trying to get through the building, another class lets out, and people get out of the room, and they stop right in front of you. Oh, Janet, hi, blah, 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 blah. And you're like, get out of my way, get out of my way. So, you know what I mean? You run into it like on holiday shopping in the mall, too. You get these little wandering groups and clusters of people that just, they find the most congested area, and they stop there and just talk about nonsensical stuff. You're like, I got a list, I gotta go, get out of the way. And they look at you like, I don't know. That's what silicon and oxygen do. You have molten rock, and it's trying to flow. And there's silicon and oxygen in that molten rock. They are going to find each other. And they will bond, and they will cling to each other. And they will make all these little floating groups and clumps and clusters. And the remaining elements, the remaining liquid, it makes it more difficult because now the remaining liquid's got to go around all these little clusters. It clumps it up. It's like putting cornstarch in a gravy, it thickens it. So if you have less, the less silicon and oxygen you have, the better. If your silicon and oxygen content is very, very low, you have fewer clumps. And that will allow for easier flow. In composite volcanoes, if one has viscous material, that's telling us that in addition to the temperature, we have a lot more silicon and oxygen. At least 50% silicon and oxygen or more. Any questions? Well, let's see. We have our list of 4 molten rock. Ultramafic we really don't see as volcanism anymore because the Earth is too cold. Ultramafic volcanism would have occurred very early on in the Earth's history when the Earth was much, much hotter It's not that hot anymore. So we're not going to see any real ultramafic volcanoes. But of the three that are left, which one of these is probably most likely to produce shield volcanoes? The mafic. The mafic, high temperature, magnesium and iron rich. This is going to be shield volcanoes. Mafic. Hot. Low silicon oxygen, high magnesium iron. Intermediate. What type of volcano is it most likely to produce? Composite. Intermediate, medium temperatures, half and half on the silicon iron. Medium temperature. Which of these can form composite volcanoes? The Composite as well. Low temperature, feldspar, and silicon. Very high is silicon and oxygen. So the different types of molten rock are going to give us different types of volcanism. And these volcanoes are going to behave rather differently from each other. A big control on the dangerousness of a volcano. In geology, we call it the explosivity. Its potential for an explosive eruption. The explosivity is in large part determined by gas. All volcanoes have gas. It's their diet. Depends on what molten rock formed them. But all volcanoes have gas. Most of that gas is going to be steam. It's also going to be a lot of carbon dioxide and a lot of sulfur dioxide. Some volcanoes have more of one than the other. Some volcanoes are going to be known for their carbon dioxide output. Other volcanoes are known for their sulfur dioxide output. Each has very different consequences on the environment. Volcanoes in general are the #1 natural control of global climate. Some volcanoes erupt carbon dioxide that maintains a warm climate suitable to support life. Without that carbon dioxide in the atmosphere, we'd be frozen. We'd be much like Mars. It'd be too cold to support life here. Other volcanoes produce sulfur dioxide. Sulfur dioxide prevents heat from coming in, so it tends to keep climate cool. So it acts as a balance on climate. Of course, the human activity throws a wrench into everything, throws everything off kilter. So that's kind of the problem we're in now. But now, if we have a major volcanic eruption that emits a tremendous amount of sulfur dioxide, we might be thankful for global warming because we'll need it to offset the cooling that could occur afterwards. But you never know. It's a spin the wheel thing with nature. Something like Yellowstone National Park erupts, and that could change global climate in a weekend. Yay. Gives you something else to worry about on the materials. Is there any questions? Yes?
What kind of volcano do we find more often?
They're both about 50-50. They have a pretty good equal distribution. Composite volcanoes, I would think, are probably a little bit ahead of shield, but not by much.
You'd say that shield is more dangerous than, right? Because the kind of rock in it is hotter?
No?
No? Are they both equal then?
Oh, no. They are no way equal. Who here has used the microwave to warm up? Well, I mean, let me finish my question. We've had microwaves since 1940 something. Who has used the microwave to heat up, boil a cup of water for tea or coffee? I don't know if it's no big deal, right? No, she is boiling, open the break a bunch of steam, stuff. Who here has microwaved a potato without putting holes in it, or a hot dog, or warmed up a nice bowl of chili without a lid? Yeah. Usually you do that once, and then you hear this poof, you're like, oh. Then you're spending 2 hours cleaning the inside of the microwave. That's gas. The water is non-viscous. So when it boils and that steam is produced, that gaseous steam can bubble through and escape that liquid very easily. In the chili, or the hot dog, or the potato, unless you put an outlet in there for that steam, that pressure is going to build. Because those materials, it's made right, that chili is viscous, it's thick. So when the liquid and it boils, it has difficulty escaping. It builds pressure. So when it does escape, it does so explosively. And that's what's going to make these two volcanoes very significantly different. Shield volcanoes, loose, runny, non-viscous. It's very hot, definitely. You have shield volcanoes in Hawaii. Mount Kilauea, Mount Mauna Loa, they are shield volcanoes. And they are almost in constant eruption. And they erupt huge columns and sheets and walls of lava, sometimes 300, 500 feet high. And there are scientists, volcanologists, in their asbestos, their shiny asbestos suits with their gear and their samplers, and they're taking samples of lava. I mean, they're not there for long, it's very, very hot. And they're taking pictures, and they're 500 feet, 1,000 feet away, and they're gosh, it's hot. Yeah, that's enough. And enjoying that beautiful eruption. That high temperature, non-viscous, whatever gas, just comes right out. You cannot stand within a mile of most composite volcanoes and watch that eruption. You may start with ooh, but you're not getting to ah. You're not going to make it. Thicker, higher density, more viscous material, you're boiling the chili in the microwave without the lid. The gases are going to build pressure. When they finally come out the top of that thing, they're going to explode. Mount Krakatau exploded in Indonesia back in the late 1800s. That sent a shockwave around the earth twice. Okay. That sound of that explosion was heard reportedly up to 5,000 miles away. It was massive. It sent tsunami across the global ocean, killed an estimated tens of thousands of people. It's still active. Krakatau, that's sweet. Krakatau is a supervolcano. And there is, of course, it blew itself, all the smithereens process. But there is a new volcanic island forming in the old crater of Krakatau. And it's called Anak Krakatau, which in the local language means the son of Krakatau. Oh, I know, that's not ominous at all. Of course not. No, it's there. But the reason why it's so Santorini in Greece blew itself to living pieces, another supervolcanic center, and it's because of the gas pressure. Gases couldn't get out, they can boom.
So based on the two types of volcanic, those two things that we're discussing, in relation to geographic locations, are they more centered to certain areas? Or
Yes, they are.
How's that determined?
Plate tectonics. Of course, we know that now. It's plate tectonics. And I'm going to get to that next. Are there any questions? We need a volcano at like Maine 3rd. Think of what that would do for tourism. We would have to go all the way to Bell Fountain to ski. It'd be cool.
That's what it would be for heroin in the area.
Yeah, there you go. It'd be a nasty traffic circle around it. I think it'd be cool. For some geology. Until it exploded, then that would be problematic. But then we'd have no class, because the volcano would be around there. So that would be bad. But there are always perks if you look at it hard enough. So let's look at where volcanoes end up. Volcanism, Putinism, plate tectonics. We'll start with divergence. Remember, at a divergent plate boundary, plates are separating. They're moving away from each other. This process is most likely found on the bottom of the ocean floor. This is your seafloor spreading. We have our oceanic crust in the ocean. What is underneath the crust? What do we call the part that's underneath the crust? The what? It starts with an M, it's not magma.
Mantle.
The mantle. Underneath here, we have the mantle. What rock is the mantle composed of? If you listen carefully, you can hear the music. I'll say things only I know for 200 Alex. Peridotite? I knew that was on the board last Thursday. What family does peridotite belong to? What molten rock is peridotite formed from? Oh, come on. Ultramassive. Yeah, I was trying to build a little thing, with bivalve.
Would be all.
Man, ultramassive. Ultramassive. So it's very hot, but solid. Hot and solid. Hot and solid. When these plates separate, they slide away from each other. That's creating a loss of pressure. It's just like if you split your skin open. You're going to drop the pressure and stuff's going to come out of the opening. Once we release the pressure, decreasing pressure leads to what? Another M word. N-E-I-N-G. With an L in the middle. Melting. Right? So this is already hot, and we drop the pressure, it's going to melt. That melts and rises up in the middle. When that re-solidifies, it solidifies at a lower temperature. That's going to form massive rock. The rock of the ocean floor, the rock of the oceanic crust, is mostly mafic, gabbro, and basalt. That's going to mean that the oceanic crust is dense and sinks to the bottom. It's really low in the mantle, so that makes it a low spot covered in water. What kind of volcanism are we going to get on this divergent boundary? Shield. Because we have mafic material being formed there. So we'll have shield volcanoes on the ocean floor. Those don't really impact a lot of human civilizations. They are erupting all the time. They don't really make the news because they're 6 miles, 4 miles deep under the water and no one really knows about it. Occasionally they will make the news because the island nation of Iceland, as a little speck between Greenland and Europe, sits on the mid-Atlantic ridge. So it is, in part, a collection of massive shield volcanoes that have been building there for so long that they've gotten tall enough to make an island. That island's growing a little less than about an inch a year. So that's going to be shield volcanoes. There's another place where we can get this happening. Question?
Are those considered drifts?
Yes. If this were to occur on land, if this would occur on a continent, that would be a continental rift. Now, continents throw a little bit extra in the mix. For example, the East African rift, where Eastern Africa is tearing away from the rest of Central Africa, we have a mixture of both shield volcanoes and composite. Because there are some areas in the rift where it's open all the way through to the bottom, and the mafic material comes right to the surface. There are other places where it's not broken all the way through yet, so the mafic comes in, but it mixes with some of the continent, and you get more of a 50-50. So in continental rifting, you'll get a mix of both shield and composite. Mount Kilimanjaro is a composite volcano that's still active. That's, I believe, the tallest peak in Africa, right smack on the equator. So also, not only is C4 spreading, but also the continental rifts. Continental rifting is not as common as C4 spreading, at least not today. Any other questions? Yes.
The drawing you put there, would that be like the mid-ocean ridge thing?
Yes.
Okay.
That's your mid-ocean ridge. That heat is going to cause that to be elevated, and you're building volcanoes there. So it's going to be higher because you're literally building volcanic mountains there.
That makes sense. That's considered, is the mid-ocean ridge considered the same as the mid-Atlantic?
Well, it's a mid-ocean ridge. There happens to be one down the center of the Atlantic. So that's called specifically the Atlantic ridge. There's also one through the South Pacific and through the South Indian. So in general, it's mid-oceanic and per ocean specific. Yeah.
So at the bottom part where it's crust, you kept going down with it. Is that where the trench thing would be? The trench? Can you talk about trench?
No, trench could be at the other end. Go get the trench.
Oh.
Trench would be over here.
Yeah, that's what I meant. Wait.
Yeah, over here. Yeah, here or on the other side or on both. Yeah. I left those off because that's part of something different. Any other questions? Well, where else can we get molten material from the mantle? Well, we have a hot spot in an ocean. That hot spot is underneath oceanic crust. Here's our oceanic crust. Our ocean. Here's our mantle. Now that hot stuff is coming up like a plume, like just a jet hot coming up here. It's hot. And it will melt its way through that ocean floor, which is massive. And it will form volcanoes. What kind of volcanoes is that going to produce? It's coming from the mantle, and it's melting through massive ocean crust. We'll get, if you melt chocolate, what do you get? You melted chocolate. If you melt massive rock, you're going to get what? Melted massive rock. You get molten massive rock. What kind of volcanoes are you going to get here? Shoot. Anytime you're going to melt the mantle, or you're going to melt the ocean crust, you're going to get massive. It's a pretty good rule of thumb. We have an ocean hotspot in our country. We call it Hawaii. Hawaiian Islands are oceanic hotspots. They are some of the tallest shield volcanoes in the world. They're over 7 miles high when measured from the ocean floor up. That's taller than Everest. Of course, Everest is measured from sea level up. And you can watch the eruptions in Hawaii because they're very gentle. They can produce a lot of lava. You got to stay away from that. But, you know, gases escape very easily. They're not really all that explosive. They're just pretty to look at and stay out of their way. That's about it. Okay, well, then let's look at the other end of that plate. Let's look at the trench. You have a trench because you have a convergent boundary. To get volcanism, we need something to melt. At a convergent boundary, the only way you're going to get melting is if you jam one of those plates back in the mantle, where the temperatures are higher. So we need subduction. Composite. Subduction. That subduction process is pulling in with it a lot of water. Water's going to make it easier for this to melt. This can melt at medium temperature because the water will decrease the temperature needed for melting. We call this partial melting. It doesn't quite get hot enough for that entire ocean crust to melt. It goes much deeper. But it'll start melting because of the water content. And that melted stuff is lower density. It's going to want to rise. That melted stuff will come up. As it comes up, it's melting its way, it's assimilating, through the continent. Continent's more intermediate, more felsic. So by the time this reaches the top, you're going to have an intermediate lava. What kind of volcanoes is that going to form? Composite. Oh boy. Where do we have subduction? All along the west coast of South America. Most of the mountains of the Andes are active volcanoes, some of them very nasty. Southern and southwestern coasts of Mexico and Central America, some very nasty volcanoes. Outside of Mexico City is Mount Popocatépetl. Just say it really fast. Or do what most scientists say, just call it Mount Popo. Mount Volcanoes is a huge ash producer. It erupts and produces just a bunch of ash. It spits dust all the time. Surrounding the Caribbean, all of those cruise ship islands. They're islands because they are composite volcanoes that have built up from the ocean floor. So, you have St. Lucia, St. Kitts, St. Martinique, you've got St. Thomas, so you got all of those, St. Vincent, all of them. Even Cuba, Haiti, Jamaica, those are volcanic islands from subduction. In our own Pacific Northwest, Northern California, Idaho, Oregon, Washington State, those are composite volcanoes, Mount Shasta, Mount Hood, Mount Denali. Through southern Alaska, the Aleutian Islands, those are all sometimes dangerously eruptive volcanoes. Mount Denali, I guess officially back to being called Mount Denali, used to be Mount McKinley, used to be Mount Denali. They did, and there's a big thing about it. I really don't think President McKinley cares. Dead. Matters to him. But, Mount Denali, tallest peak in North America, it's over 22,000 feet tall, is an active volcano. Japan, those islands exist because of volcanoes built by subduction. Mount Fuji, Mount Unzen, some of the world's most dangerous volcanoes. I don't know what it is about Japan. They get nasty composite volcanism. They have tsunami-producing earthquakes. They get landslides. They get devastating typhoons. And then they do what? Invent Godzilla. Like they don't have enough problems. But Godzilla you can fight. You can't fight nature, so maybe that's part of it. The Philippine Islands, those are all composite volcanoes. Mount Pinatubo erupted in the early 1990s, quite devastating. Indonesia, throughout Indonesia, there are some here, and then the rest of them are over here. Throughout Indonesia, there are over 180 volcanoes. They're all composite from subduction processes. We got some composite volcanism again in the East African Rim. We got some composite volcanism here through the Mediterranean from subduction. Mount Etna is gradually becoming a subduction volcano. Mount Vesuvius in Italy is a composite volcano. That's the one that blew up in 79 AD and killed all the people in Pompeii and Herculaneum. Of course, it figures. The deadliest type of volcano is where all the people live. Yeah, that's how that happens. Figures. Now, if that's not bad enough, if we look at hotspots under continents, we have an extra problem. This is what we run into in Yellowstone. That is a continental hotspot. That's rising up through there, and it's very hot. But it's in the middle of the continent. It's under land. It's under 60, 80, 90 feet of rock of the continent. There's no water source there. So water is not going to help with the melting. So without water to help, it's going to get really, really hot. That really, really hot stuff has to melt its way through as much as 60, 80 miles of continent to get to the surface. That really, really hot stuff is going to melt the intermediate and felsic material very, very easily. What comes out eventually is felsic. That felsic material at that hot spot is low temperature. That material has lost a lot of its heat coming up from 60 miles below. It's very low temperature. It's very silicon and oxygen rich. It's got a very high viscosity. And it will explode the kingdom come when it comes out of there. That's one of the reasons why Yellowstone is considered a supervolcanic center. It is dangerously explosive. An eruption from something like Yellowstone will have global consequences.
They say it has the potential to wipe out like 7 states or something like that.
Easily. Easily. We will get ashfall here in Ohio from Wyoming, anywhere from a few inches or more, because the wind blows from west to east. Pretty fantastic. So if you're outside and like camping equipment starts falling out of the sky, you'll know that Yellowstone.
Hollywood.
Yeah. Won't be quite that bad. You're not going to be in a Winnebago trying to get away from that. Not going to happen. So, yeah. Super volcano. Are there any questions? Because, a supervolcano blew up in Indonesia, Mount Toba, still active. Mount Toba erupted about 75,000 years ago. And volcanologists and other geologists noticed that this eruption had occurred in the geologic record because they found up to 2 feet or more volcanic ash from the floor of the Atlantic Ocean, some 4,000 miles away from that eruption. So something happened here. And they were able to catalog and notice in the geologic past that when that occurred, there was a definite change in global climate. The volcanoes of Indonesia produce a lot of sulfur and sulfur dioxide. That causes temperature drop, causes global cooling. Can be a condition that lasts for several decades. Without proper sunlight and lower temperatures, that crashes your plants. You lose your food chain. And so they had this big, they put everything in paper, they went to a big scientific conference, they presented their paper. Oh, yeah, that was awesome, wow, cool, yeah. Well, they had some colleagues of theirs that were also presenting. So they went to go see their talk. And their colleagues, true story, these other people they knew were anthropologists studying ancient human civilization. And they had been working with some biologists and some geneticists. They would track the mitochondrial DNA, that's the one that goes back to your mother, and had noticed that back about 100,000 years ago, there were several dozen human family lines of early humans spreading out from Africa through Asia and whatnot. And then somewhere around 75,000 years ago, they almost get completely wiped out, and they get reduced to less than a handful. But they couldn't figure out what the mechanism was that would have resulted in almost completely wiping out the human species. And these volcanologists are in the audience going, 75,000 years ago? Is that when Toba erupted? Yeah, we spoke that paper. Yeah, oh my gosh. And so it was interesting in the same conference to realize that we almost were completely wiped off this planet. planet by the eruption of that volcano. So, yeah, it's still active. If you're bored and you want to look at something interesting, you get on YouTube and look up the Jakarta incident. It's about Mount Gyeongbong. That's another one. It's just really fast. Mount Gyeongbong in Indonesia.